Hello and welcome to this presentation on Kaku hashing. This is the final project demonstration for the course CS201 Data Structures 2. The project team presenting is Sibling Variables. Project members include Fahad Shaikh,
Asad, Tariq.
Fatima, Zehra. Neha, Valliani. Moving on to the structure in question. Google hashing is a form of an open addressing in which each non-empty cell of a hash table contains a key or a key value pair. This results in a hash table with the following efficiencies for the three common hash table operations: lookups, deletions, and insertions. The Google hashing structure combines the idea of the second choice hashing, that is, a variant of a hash table in which keys are added by hashing with two hash functions, thus giving the key two possible points of insertion in the table. Moreover, Google hashing also houses the notion of a relocation hashing. In such a hashing, the keys can be moved after they're placed. This results in the structure splitting the hash table into two subtables, which then respectively make use of two separate hash functions, hence allowing each respective new key two possible entry points in the structure. This follows from the second choice hashing. Do note that the insertion of a new key could very well result in the eviction of an existing key in the table to a whole other location. We'll talk more about this when we're analyzing the structure. Combining the two, we see that the two ideas respectively result in the cuckoo hashing structure constant time of worst case lookup by closing the gap of the average and the worst cases. This is a huge improvement over its competitors of separate chaining, which has worst case lookup of O log of log n, and linear probing, which has worst case lookup of O log n. This renders the cuckoo hash structure as the first hash table with practically small constant factors. Talking about its analysis, with regards to the analysis of the structure, lookups take constant time because only two locations must be checked. As you can see on the screen, for example, if we were to search for some particular element, we could simply inspect the two locations indicated by the outputs of hash functions of T1 and T2. Fatma will explain further analysis.
Okay, so moving on to deletions. As we know that deletion also takes constant time because there are two locations that are needed to be checked. For example, if we are looking for the number 41 to be deleted, we will hash it with the respective hash function of the table T1 and T2. We will further do the inspection of these two highlighted locations, and if 41 is to be found, we will be removing it. Before we move on to insertions, we will first look how it works. If we were to insert an arbitrary element, you will first hash it by the hash function of the first table, and if it's empty as highlighted in this case, we will simply insert it on the allocated space. Well, another case of insertion could be that the location indicated by the first hash function is occupied as shown in this case, then we will simply insert it and with the old value and subsequently rehash this into the second table. And now moving on to the most important case of the insertion, we consider the failure of such an operation. Now considering the insertion of element of 91, in this case it hashes to the location of 75 in T1. Thus we place 91 at this location and displaces 75 subsequently placing it in T2. Now if 75 were to be placed in an already occupied position in T2, in this case at the position of 32, thus this would result in a displacement as well as requiring 32 to be hashed in T1. If 32 were to hash in T1 at the position which is now occupied by 91, and subsequently 91 would map to the location of 75 in T2. Thus we would essentially have an infinite cycle of displacements among these three elements. If that happens, perform a rehash by choosing a new H1 and H2 and inserting all the elements back into the tables. Multiple rehashes might be necessary before this succeeds. Hence, insertion is amortized constant time.
Right, so moving on to the problem stage of the project, do note that our project essentially has two modules, and the first of these pertains to the mitigation of password attacks via salting. So what you should know is that in any system where you have user account details stored, passwords, as you can see in this text file here, are not necessarily stored in plain text. Rather, what is stored is a hash value representation. Right. So with regards to security, any system that does not salt their passwords are very weak, because in the case where you have two users using the same password, such as this user here and this user here. So what you'll have is essentially these two people are gonna have the same hash values stored due to the deterministic nature of a hash function. And this is actually quite poor because a potential hacker could better predict the password. So that is Lenovo Legion for this user and this user here, that legitimately maps to the hash value that was generated from this. So what is worth noting is at this point, though, before we move forward, is that while hash values are indeed quite brilliant in themselves, they are not necessarily breach proof, such that you could very well figure out that the value that mapped to a particular output of a hash function, uh, just by continually generating hashes from a entire library of random words that you constructed, and you could find and you could just basically determine the password or the piece of information that mapped to that particular hash value. This would pertain to an attack vector of what you would call a brute force attack. Other possible vectors would include something called a dictionary attack, and you could very well actually use a hash table itself to actually have a much faster brute force. Now, through this first module of our project, what we essentially do is we demonstrate that one could actually have greater security of their information by actually salting their password. Now, according to the Open Web Application Security Project, a salt is essentially a value generated by a cryptographically secure function. This function here is the cryptographically secure function, or so we say. I wouldn't hold that against us. I'm pretty sure an IT security specialist would rip that claim to pieces if they were to look at this. This function here generates salt. Right, so through that function, what we essentially do is we generate a 32 character value, which is of complete garbage, as you can see, complete nonsense, yet it's very useful to us because what we do is we split this 32 character value at the 16 character, that is, we split this value in half, and what we then do is we respectively append and prepend the halves of this split value to the password that the user supplies when they log into the our fake pseudo system that we've login system that we've created when they're registering into it. So essentially, what happens is that when this what happens is when this password salt mixture, that is a password which is then appended and prepended by this garbage value which is known as a salt. So we generate a hash value from this, and it looks something like here. And this hash value, as you can see, is actually unique for each particular user, such that each particular user actually gets their own unique salt. Thus, the append salt password mixture is in itself specific to the particular user when they were logging in. Hence, you essentially have a one-to-one correspondence between a user and the generated hash value, rather than the previous case where people who had the same password will essentially map to the same hash value. That followed from the deterministic nature of hash function, as I previously said. So for the purposes for our module, what we do is we make use of the hash table structure as essentially a pre-computed database of hashes, as we're essentially inserting these hash values into the database itself as we've already computed them beforehand. And essentially what we're doing it is when we're inserting them into the database, which we actually calling the structure itself. And what we essentially do is we use this username here on all these as a key for our records, and the value is essentially a tuple which actually houses this random salt for that particular user when they signed in, together with the hash value that generated from their password salt mixture when they registered into the system. So when the user is actually logging back into the system, as I'll show you for this person, Right, for this person, Don Vizela with the password Lenovo Legion. So what happens is we essentially perform a find operation on the structure, where on this key here, and provided this user is indeed valid such that this user was registered to the system, we get a, uh, we essentially have a row returned from the structure itself. That is the tuple from the key value pair. Now what we then do is, we're gonna take the salt that was in that tuple that was specific to the user when they registered into the system, and we're going to take this password which is provided with the user when they're logging back into the system after some time, and we're going to do the same pending prepending process, and we're going to again generate a random hash value from this current salt password picture. And now what we're going to do is we're going to take this sort of currently generated salt password mixture, and we're going to compare this against the hash value that was stored when the user was registered into the system. Now, if these two hash values indeed matched, thus the user will be able to successfully log into the system. Hence, they were verified such that this is the user itself and the password is indeed correct. So, moving on, Asad, on to you for module 2.
Okay, the second module of our project is basically a schedule verifier. Its purpose is to basically construct a timetable for a particular choice of classes as selected by the user from a pool of different classes, which you can see on your screen right now. So choosing classes on the same day that have exactly the same timings or overlapping timings should essentially cause an error, and the user should not be able to enroll in such classes. The solution that we came up with for this problem was an efficient way to check the user's proposed schedule. To implement this solution, we use cuckoo hashing and store the different classes of the schedule with their respective times as the keys and the details of the classes as the corresponding values. Now, the very fact that our data structure does not allow for duplicate keys weeds out all the classes in the hash table that have exactly the same timings on the same days. Now we only need to manually take care of overlapping conflicts for the remaining keys in the hash table to fully verify that no clashes occur. The result of the schedule verification is then displayed to the user that whether or not their proposed schedule was conflict free, or if it had any conflicts, they will be identified to the user as you can see on the screen. This basically concludes the second module of our project.
Right, so moving back to our presentation itself, Asad, on to you for research.
So the finalized list of references that we have used so far in our project for cuckoo hashing is as you can see on your screen. And moving on, the teamwork is as divided in the table as you can see. The allocation of tasks was given differently to everyone, as you can see the breakdown over here. And moving onwards, that brings us basically to the end of our presentation. And feel free to ask any questions if you have any. We'll be glad to answer them. Thank you.
And also, furthermore, if you would like to see something from the breakdown that was given in the teamwork, such as the verification of the structure or the like, please don't hesitate to ask. Yes, so thank you for watching. I hope you enjoyed it.